All right, so let's start with our first example. In this first example, the idea is that we want to test 3 different driving routes between where you live and where you work. So in this example, let's suppose that someone lives in Carlisle and they work in Harrisburg, and they have a bunch of different ways they could get there. Like they could hop on the turnpike and go straight downtown and then pop off the turnpike or when they get in, or maybe they could take I-81 and come across the top of Harrisburg, or maybe they go down Route 11 on the Carlisle Pike and sort of go through that way. Like there's a bunch of different ways they could get from Carlisle to Harrisburg, and they want to know which is fastest. So can't just look at how long the routes are because there's different speed limits and different amounts of traffic. So they decide to test it. So we're going to test each of the routes. And we aren't going to just drive each of them once because there might be good days and bad guys. Good days and bad days. We're going to drive each route a bunch of times. So here's the times that we got for route 1. So the first time we took the first option, it took 22 minutes to get from home to work using the first route. And then the second time was 21 minutes, and then it was 35, and then it was 30. So you can see there's good days and bad days. And then here's all our numbers for route 2, and here's all our numbers for route 3. Now notice the last box here for route 3 is blank. Is that because I missed typing something? No, it's just that we only tried route 3 7 times, whereas we tried routes 1 and 2 8 times. That's okay, the test is still going to work. We're just going to compare the sort of the mean and standard deviation of the data we have, and it's possible that some of the groups will have more data than others, and that's fine. ANOVA can totally handle that. Also notice this data isn't sorted, smallest to largest. I have had a lot of students in the past think that you have to sort of put the data in order for the your software to handle it, and it doesn't have to be in order. You just have to make sure this software understands which numbers are in which groups, and that's enough. So we're going to take this data, and I'm just going to copy it, and so I'm going to highlight it, copy, and then we're going to go paste it into Minitab. So we'll flip over to Minitab here, and paste. And I kept the column headers, and Minitab is smart. It realizes that there are column names, and should I move it up so that the column names are in this blank section and the first row of actual data is in row 1, and I actually do want that, so I'm going to say move. And so now it has the column headers in this sort of heading blank section, and 1 corresponds to the first data. And there's a little star here because that box was blank. Okay, so let's go and run our ANOVA test. So stat, ANOVA, and there's lots of different kinds of ANOVA, but we're just going to do the most basic, which is just like the one-way ANOVA. Okay, so response and response data are in one column for all factors. That's not what we have. We have the data in separate columns. So click here. Here are different columns that have our different responses. So that one with all of them in being one column, that would be like one column has a whole list of numbers, and then there's a second column that has like basically like multiple choice tags, like A, B, C, or D, or something like that. And then all the people who are tagged with an A, their number should go into like group 1. And everyone with a B should go into group 2. So you could sort of split your big pile of data into separate groups based on their answers to a second multiple choice question. So that's what you would do. That's when you would use this first option in the drop menu. But we actually have the data in separate columns already, and so we'll use that version. What do we have under options? Assume equal variances. I haven't been doing this in the past, and I guess I'm going to continue to uncheck that. But like, if that's checked, like your answers change a little bit, but not very much. It is going to generate some kind of confidence interval, it looks like, but that's not going to be something that we're going to try to interpret here. Comparison, this is sort of like altering the test in ways that we're not going to talk about, and I don't really understand, so we'll just leave those as the defaults. What about graphs? interval plot, individual value plot. I like the interval plot idea. And histogram of residuals. I don't want to really see these residual plots. So let's just leave it the way it is. And it looks like it's going to give us some kind of picture here, though, to go with our test. So let's hit OK and see what we get. Okay, null hypothesis, all the means are equal. Alternative hypothesis, not all the means are equal. We have a significance level of 5% is set. And there's a bunch of different numbers that are computed here. F value, p-value is what we care about, right? So that's bigger than 5%. So we are not rejecting the null hypothesis. It is still possible that these roots are all equal. The means are all equal anyway. The F value is kind of like a measurement of the comparison between how wide each of the bells are and how separated the bells are from one another. Other times that I've taught this class, I've sort of gone through the computation of how that works. It's all in the book, but I don't want to bother with it with this online class business. Looks like we have a 95% confidence interval for each of the individual roots. So this is sort of like where we think that each of the roots are. And so there's a picture of like how the roots compare here. So the first root, as far as we know, the real mean is somewhere along this line between like 22 and 30. And the second root, its mean, the confidence interval we got for that is sort of from 22 to 28. So I said it before in terms of bell curves. So you could imagine there was like a bell here, and like the extra 5% that's left out of the 95% confidence interval is down here and up here. And there's a bell here and a bell here. And so these bars are sort of like the main part of the bell. And you can see they overlap a lot, right? Like there's sort of this section in the middle between like 25.5 and 27 that is in all three intervals. And so maybe the true mean for all three of them is like at 26. So it's entirely reasonable that the actual mean for all three roots is 26 minutes, and the null hypothesis is true. So that's why we got a p-value that was bigger than 0.05, and we didn't discount things. So or we didn't say that there's any evidence that some of these are different. Okay, so that's why it's called analysis of variance. It's comparing how wide these intervals are compared to how much they shift up to down. So this one's down and this one's up, but it's not up enough to make it so that these two intervals don't overlap anymore. And that's sort of like the idea of how this test works. But the main idea is that you're taking quantitative data, you split it into more than two groups, need a way to compare them, that's ANOVA, and it unfortunately locks you into this null and alternative hypothesis, but it runs on any number of groups. Okay, so let's end this example and do a couple more examples.